In this lecture, we study about power cable technology and fundamentals of cable insulation materials. So, let us see the evolution of cable insulation materials. So, in early 1960s, oil impregnated or oil filled cable insulation. This is actually the first cable systems. Usually covered with lead sheath to prevent moisture ingress. They are normally covered with lead sheath. The cable is covered with, after insulation, lead sheath will be there to cover that, and used in low to medium voltage applications up to 33 kV for this oil impregnated paper. And oil filled can be used for high field application actually, extra high voltage up to 800 kilovolts also the oil filled cable has been developed and is in use. And in 1960s, 70s, this is early 60s, during 60-70, high molecular weight polyethylene has come into picture. Here, this is a thermoplastic insulation. Means, it can be recyclable. It can again be used for some other purposes. So, but this is also less susceptible to moisture compared to paper actually, and less dielectric losses when compared to paper insulation, and is lightweight. But premature failures observed due to water treeing. It's a phenomenon actually. From this conductor side, slowly a tree-like structure develops from here, and it can even happen from this outer insulation side also into the insulation. So it is since it is basically due to water, so that is known as moisture or water. It is known as water treeing. So this kind of phenomena has been observed and causing premature failures. These are used up to medium voltage applications, up to around 66 kilovolts. These cables are successfully used. And then in early 70s, cross-linked polyethylene has come into picture. We will see what is cross-linking and all. So all, for this also base material is polyethylene. For this also the base material is polyethylene. So cross-linked polyethylene, what it is. So we will see later what it is. But this cross-linked polyethylene is actually thermoset. It is non-recyclable. If you heat it, it will in fact, it may become carbonized, but it will not melt, and then you cannot use it again. So that's how the cross-linked polyethylene will be. And it is slightly higher dielectric losses compared to this HMWPE, high molecular weight polyethylene. But lot sensitive to moisture, less sensitive to moisture. So compared to HMWPE, this is less sensitive to moisture, and used for medium and high voltage application up to 132 kilovolts successfully. But of course, even higher voltages is also available, XLPE now. Susceptible to electrical treeing and aging due to space charges. These are the issues. Aging due to space charges is mainly under DC, and electrical treeing will occur inside the insulation. So this is electrical treeing, means it's a process we will see later maybe in the next video. So already I have shared first video that itself has everything actually. In that also you can see what is electrical treeing. So this material is susceptible to electrical treeing and space charges. And in mid 1970s, EPR, ethylene propylene rubber insulation, and EPDM, ethylene propylene diene monomer. So this insulation has come into picture. High dielectric losses, but less susceptible to moisture compared to XLPE or tree retardant XLPE, the next one. So this is having high dielectric losses, but less susceptible to moisture. So requires inorganic filler additives. They need some inorganic filler additives such as MgO, etc. Are essential for this. So used for medium and high voltage application up to around 132 kV successfully used. Even beyond that voltage also successfully used. But susceptible to electrical treeing again and aging due to space charges is also there in this kind of insulation. So tree retardant XLPE, TR XLPE. So dielectric loss is slightly greater than XLPE, greater than this, but less than EPRs, less than this, and less moisture sensitive than XLPE. Used for medium and high voltage applications up to 132 kV or more, but more susceptible to aging due to space charges. So compared to these, it is more susceptible to aging due to space charges. So then for DC application, it is not so good like XLPE, because DC space is affected by space charges, and since TR XLPE is more susceptible to space charges, then of course tree inhibition is also very important, but under AC treeing problem is more problematic. So these are the three different cables shown here. PILC, paper insulated laminated cable. So here this is paper. Normally it is polypropylene is used, tapes are used for laminating this paper. So that kind of cables are called PILC cables. And XLPE cable is cross-linked polyethylene. Basically, the base material is polyethylene, but it is cross-linked. So this white portion is XLPE insulation. And then ethylene propylene rubber. So this is EPR insulation. You can see here. So just above the conductor, this EPRs are used here. So these are some types of cables shown here. And then physico-chemical properties of cable insulating materials. Let us see what they are. Basically, polyethylene is base material for most of cable insulation. Recently, a SIGRE report says around 80% of the cable insulation is polyethylene now. So here this is the monomer. Monomer means C2H2. CH2CH2, these are called, this structure is called a one monomer of C2H4. So if we polymerize this, poly means many actually, many such units, if they form like chain, then that is phenomenon known as, process known as polymerization. So this is a polymerized polyethylene actually. This is polyethylene it is called. This is ethylene and this is ethylene monomer. Ethylene monomer, when it forms a chain like this, then it is polymerization or polyethylene it is called. Of course, this does not depict the actual chemical structure and its complexities. We will see that also soon in the next. So for polymerization, heat, pressure are catalyst. There are several processes of polymerization that also we will see. So polyethylene is our actually base material for most of the cable insulation nowadays. So now this is a straight polyethylene chain, looks like this actually. This is how a straight polyethylene chain without any branches or coiling or anything. A simple straight polyethylene chain. You can see here these black spheres correspond to carbon and this white sphere correspond to hydrogen. So each carbon atom has two hydrogen here, and then it is also having bonds with another two carbon of the adjacent carbons of adjacent unit. So this is how it will look like, a polyethylene chain, and you can see the complex structure here, which is actually They can coil up, they can branch, several possibilities are there. Here you can see how this is the main chain, how it coils up, and can be seen here. This is depicted here again. So this portion is zoomed here like this, like this, like this, and then like this. So this is how this small curvature can be seen here. And then they can coil up like this, also branches. So this is main chain actually, single chain. This is a molecule of linear polyethylene, or called HDPE, high density polyethylene, without any branches. Simple chain like this, straight polyethylene. So this is called HDPE, or linear polyethylene, but it also branches like this sometimes. So these branches can come from any carbon molecule or any hydrogen molecule. So they can come like this, and then open end branches. This branch terminates here. Actually, it terminates in CH3 kind of thing. We'll see soon. So a molecule of branched polyethylene, or LDPE, low density polyethylene. So this is HDPE is a linear chain, and LDPE is a branched chain like this. So this is how the typical structure of polyethylene will look like. And then intermolecular forces determine the physico-chemical properties. This is a polymer chain. So if within the chain, if you have different molecules, and the forces between different molecules are called intermolecular forces. But if the forces are between two adjacent carbon or hydrogen units, then that is called intramolecular. This is intermolecular, this is intramolecular. So the primary forces, but the bond energy in intramolecular forces are very high, actually 100 kilocalories per mole, very strong, while that intermolecular forces are just 5 kilocalories per mole, weak. And bond length also, this is 1.5 angstroms, this is a little bit more, 3 angstroms. And the type of bond is covalent, and in this case van der Waals are hydrogen bonds. Let us see in the next slide what they are. Influence and chemical structure and molecular stability is the influence, and physical chemical properties depend on these intermolecular forces. And TG, the glass transition temperature or melting temperature, solubility, etc. are dependent on these intermolecular forces. Now a quick look at various intermolecular forces. These are van der Waals force depicted here, and this is hydrogen bonds depicted here. So this is a simple atom which has central positive charge and surrounded electron cloud with negative charge. And this is again a simple atom. When they are far away, there is no problem, but when their distance is 5 nanometers or less, then what will happen? This electron cloud gets attracted by this nucleus, then the structure becomes like this. This electron cloud is attracted by this one, so there is slight change in the structure. Then these form actually dipoles here, and there is some attraction, some force of attraction will be there. So when two atoms come within 5 nanometers of each other, there will be a slight interaction between them, thus causing polarity and slight attraction. So this is how van der Waals forces will be appearing in the material. Then hydrogen bonds. Hydrogen bond is the electrostatic force of attraction between a hydrogen atom in one group and more electronegative atom like O, N, F in another group. Of course, not relevant for polyethylene, but here you can see in nylon polymer. So how this is oxygen here, this red one is oxygen, and it is having a bond with this hydrogen. So this is how intermolecular forces will happen in a hydrogen bond. So yes, then chain length and molecular weight, how they are related. There are various ways of calculation actually. Here the simplistic approach. Size of a monomer is m, and then degree of polymerization is n. Then maximum possible length of the polymer is simply m multiplied by n. This is the simplest way of calculation. But this kind of approach is not possible because maximum length can never be realized. This maximum length can never be realized. A polymer has lots of degrees of freedom. So this is why, therefore, this approach is not so straightforward. There is another approach here, linear chain approximation. So here this is we consider the polymer is having simple linear chain without coiling and all. So what is the length, total length? Actually, if this angle is a, then a by 2 if you consider, this length divided, multiplied by cos a by 2 is the length in this direction, in the polymer direction, chain direction. So total length can be estimated L equals to m into n into cos a by 2. So this is a more realistic approximation, valid for linear chains, only for linear chains. If the chain is like this, then without any branching or coiling, then it is applicable to such a linear chain. But still does not take into account for coiling. But actually the chains will coil like this, then therefore this kind of approach is also does not take into consideration this coiling. So there is a random walk model actually. L is actually taken as a function of m and n. So actual length is determined like this. That is, of course, is not in the scope of this subject. So you can, if you are interested, you can go through the middle. Lot of material is available online. Now, chain length is related to molecular weight actually. More number of monomers means more molecular weight and more coiling. So, polyethylene is not a single coiled chain. It is branched out. Hence, we need to consider distribution of different chain lengths, molecular weights, average molecular weights need to be defined. So, this is what is important. Then let us see what is number average and weight average. If number of molecules of ith type are Ni, and mass of each molecule is a molecule of ith type is Mi, so the total mass of all molecules in ith type itself is Ni into Mi. So total mass of all such molecules of all types. So we have sigma is equal to 1 to n, Ni into Mi, where n denotes the number of types of molecules. So from this the number average of mass is given by Mn, which is equals to total mass of all molecules of all types divided by total number of molecules of all types. So this is how the number average of mass is obtained. And then there is another is weight average. The weight fraction denotes the fraction of total mass represented by the ith type of molecules. So it is a weight fraction of a particular type. So like that, ith type Wi equals to Ni into Mi divided by sigma I is equal to 1 to n into Ni into Mi. This is how it is defined. Now weight average is simply the sum of all such weight averages multiplied by their Mi. So sigma I is equal to 1 to n Wi into Mi is weight average. Normally the weight average will be more than the number average of the mass. The polymer is usually characterized by its Mw by Mn ratio. If it is unity, that means that it is perfectly linear. That's what it is. So the higher the ratio, the higher the branching, weight dispersion. So it indicates the branching, how much the polymer is branching on that. So this is how actually a polyethylene, this is a typical molecular weight distribution of a polyethylene. So molecular weight is given here, and then this is where the Mn falls and this is where the Mw falls. So this Mw is slightly higher than Mn. How to calculate Mn and Mw? There is a demonstration here. You can see blue type, yellow type, green type, red type here, type of molecules chain. Then there is number here, Ni and Mi. So from this table you can calculate Ni and Mi in this column, and Wi can be calculated in this column using this formula. And then sigma I is equal to 1 to Ni, total number of molecules is 1 to 1 plus 2 plus 3 plus 4 is 10. And similarly, sigma Ni Mi is this sum of these is 100 and Ni into Mi, Ni into Mi. This sum of these is 150. And then Wi into Mi again. Wi into Mi, 5 into 5, 25 by 150, etc. If you compute like this. This comes out to be 16.67, the weight average, and then the number average comes out to be 15. So this is how the typical calculation can be done for number average and weight average of mass. Now coiling. So you have seen why coiling actually happens and all. So there is actually a fixed, all the bond angles around each carbon atom is in the backbone are 109.5 degrees actually. This is 109.5 degrees between each each carbon atom in the backbone. Now all the bond angles, this bond, this bond, this bond, this bond. So it forms actually a tetrahedron like this. The groups around the central carbon atom form the vertices of a tetrahedron. So the chain can continue from either of the three ends as shown here. So it can continue, and then hence there are three conformations possible for each single ethylene monomer. So this is how then the polymer, hence for polyethylene, it would be 3 to the power of n conformations. That's why the polymer chains coil or bend depending on polymerization process. You can see the three-dimensional structure of this one at this website. You can see the three-dimensional model of polyethylene. Please go through that one. So let us please go through that one yourself. Then branching. Polymerization can sometimes happen to the more than one end of a tetrahedral monomer. This leads to branching. So here this is a linear portion. You can see chemical structure CH2, 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 CH2 like this. This looks like this only, where this one is carbon as indicated, this is hydrogen. So this is a linear structure, and branched structure looks like this. So whenever there is a branching CH2, the last one is CH3 because it has to terminate. One bond will remain, so where the another H molecule will be there. So this is how the branching will be there in the polyethylene. Now it is possible to control the length and distribution of branches by polymerization process. There are actually several processes by which polymerization can be done. So it is actually possible to control the length and distribution of branches by different polymerization processes. The significance of branching is that their length and distribution affect the physical properties and also influence the ability to satisfactorily extrude the polyethylene. So the significance of branching is that their length and distribution affect the physical properties. So how much branching is there, what is the length of these branches, determine the physical properties of the material, and they also affect the extrusion. Extrusion means the manufacturing of polyethylene. So polyethylene means how the material, insulation material is laid on the metal conductor. The process, the manufacturing procedure is called extrusion. So actually what is done is it will be heated and melt. So the melt polyethylene will be laid on the cable in a structure, in a mechanical structure known as extruder. So this extruder, through which continuously the central conductor is pulled out, and then while it is coming out, then the insulation is laid on the conductor, which is uniformly and in a cylindrical fashion the cable will appear. This process is known as extrusion process. And extrusion process, satisfactory extrusion means, the extrusion process should not be lead to any problem in the structure of the insulation there, and it should not have any trouble in extrusion means, if the material is very hard, then extrusion becomes difficult. So for satisfactory extrusion also, the physical properties do affect this satisfactory extrusion. The physical properties which depend on the branching will affect the extrusion process. For example, consider linear high density polyethylene like this, high density polyethylene, all chains are like this. So linear chains without any branching. So in this case, it is highly crystalline in nature. So it is, you can see how systematic they are, like in a crystalline structure. This is highly crystalline in nature. Stronger intermolecular forces and tensile strength will be there for this kind of material. Extrusion process is comparatively difficult because it is very strong. So even after melting also, pushing through the extruder, etc., and forming a cylindrical structure, cable structure, becomes difficult because of the strong nature of this material. But it has the advantage that it degrades more slowly compared to the other part. So here this is HDPE, high density polyethylene, with linear chains and with more forces between them. And this is branched low density polyethylene. Here you can see there are branches, and this structure is not in general crystalline structure, more of amorphous in nature. So this is highly amorphous in nature, but weaker intermolecular forces and tensile strength, because relatively the distances are more, so less tensile strength also. But extrusion process is very easy. So if material is strong, then extrusion process is difficult. If material is having weaker molecular forces, then extrusion process is easier. But it degrades more quickly than high density polyethylene. However, both HDPE and LDPE are vulnerable to moisture ingress, and their electrical properties are almost same. Now, crystallinity. So we have seen the polyethylene with branches is having predominantly amorphous nature, but it also has crystalline structures. Now, what is crystallinity? Understanding it is very important. Conventional polyethylene has many chains. The chains have a tendency to coil. But for polyethylene, different chain segments have a tendency to align next to each other like this. This is alignment of some chains. So here this structure looks like a crystalline structure, systematic. But this structure is amorphous structure. So for crystallinity to occur, non-branched chain segments must be able to approach each other, since the bulky nature of branching hinders alignment of chains. So this is how you can see the crystalline structure, and lamella ribbons grow out from a nucleation points to generate spherulates. I will show you in the next slide what is a spherulate. So this is how the internal structure will look like. There is an interface, there is an amorphous region. There is an interface actually between amorphous and crystalline region. This is how crystalline, amorphous, this is how it will be. So in fact, the clear structure is shown. It is even published in one of the papers of my student Avnish Upadhyay. He has just completed his PhD recently. You can see the structure here. So the polyethylene thus comprises of both crystalline and amorphous regions separated by interfacial regions. So this structure is known as a spherulite. Within this spherulite, then say this is a nucleus of spherulite, and these are spherules will come out like this. And then a zoomed portion of this small region you can see here. So inside these lines indicate actually the crystalline structure of chains. These chains are aligned like this, and then amorphous region. Between amorphous and crystalline region, there is interfacial region. So you can see this is again zoomed out in this portion. This is a crystalline structure, this is amorphous structure, and in between there is an interfacial region. Actually, it is shown in our paper that this intermediate, interfacial region has very crucial effect on the conduction processes, electrical conduction of polyethylene materials. Now, how crystallinity pertains to cable insulation? The crystalline region imparts desirable properties such as toughness and moisture resistance, whereas the amorphous regions affect the ductility and flexibility of the polyethylene, as already discussed. So, crystallinity is not affected by the conversion of polymer pellets into insulation during extrusion process. Polymer pellets means, small, round, look like tablets actually. So, all polymers actually before extrusion, they are made into pellets. Actually, these pellets are used in the extrusion process. So, these pellets can be easily packed in bags, and then they can be easily transported. And these pellets will be used and heated up. When they heat and they melt and they become together, forming a gel-like structure. And this will be fed into the extruder. The extruder will put the material on the central conductor in a process known as extrusion process, by which a cable is made. So, crystallinity actually within the pellets, whatever crystallinity is there, and then in the extrusion process also same amount of crystallinity will be there after extrusion process also. So, this sentence says that crystallinity is not affected by the conversion from pellets to cable. Based on degree of crystallinity, we can have 4 different types of polyethylene. The high density, high molecular weight, which will be used in jackets. High density, low molecular weight, again used in jackets. Low density, high molecular weight. HMWE cables used in early days for cable insulation. And of course, low density, low molecular weight is not relevant to cable insulation. Of course, temperature does affect the crystallinity of the material. Then cross-linking. What is cross-linking? So, this is actually a process. Cross-linking is a process of joining the polymer chains together as a result of certain chemical reactions. So, this is how actually polymer chains are there. If there are cross bonds like this, if they are established within the material, then that material is known as cross-linked. So, because the ends of the polyethylene branches are connected to another chains instead of just hanging loose, with temperature age, the chain won't be separated. So, the chain will be rigid, more rigid. They are actually thermoset permanently. Even if you heat it up, then they don't, these bonds cannot break, and then it is thermoset. Once they are made, then they will be more or less permanent, and then if it is thermoset, then you cannot use this material for recycling. You cannot heat it and then get it back to original thing. So, that's why cross-linked polyethylene, you cannot recycle it. Simple polyethylene can be recycled. So, this because the hanging loose ends will be tied like this. Now, cross-linked polymers hence deform much slower. They don't deform normally actually. Practically, they don't deform. Means even if you heat the cable, they don't melt and then they don't change the shape of the cable. So, their tensile strength is a lot higher than the non-cross-linked counterparts. So, high tensile strength is achieved by this structure. They have better moisture resistance compared to the other counterparts which are non-cross-linked. they cannot be recycled, restored to previous forms. This is what I was saying. And electrical properties are only marginally increased by cross-linking. So, not much difference in electrical properties, but the structure becomes rigid. So, this is how the cross-linking process will help actually. Effect of cross-linking are chain length, etc. For simplicity, consider linear polyethylene chains without coiling, and if two adjacent chains link together, we immediately see that the molecular weight has increased. It is more clear in the equivalent diagram here. So, where the first two chains are simply redrawn, the first cross-link leads to two branches like this. So, this is how the effect of cross-linking on chain length, and let us add three more crosslinks arbitrarily to two different chains. Observe how the newer or previously cross-linked higher molecular weight chain is again linked to another chain like this. So, the equivalent becomes like this. Redraw the cross-linked chains again. Notice how the chains look elongated. The molecular weights of two original chains increase dramatically in cross-linking. So, this is how and this process continues actually until all branches are cross-linked. All such branches are cross-linked. Now, cross-linked polyethylene with coiled chains. You can see here with coiled chains also there are cross-links formed here. In the previous figure we have seen linear chains only. Now here coiled chains also cross-link like that. So, okay, you can see the three-dimensional model in this link. Now test to determine a cross-linked polyethylene. So, how much is the cross-linking? What is the level of degree of cross-linking it is called. So, it is how it is estimated. Solubility in a heated organic solvent, for example, toluene, xylene, etc. So, how much the non-cross-linked chains move apart in heated solvent and dissolve, they get dissolved. And cross-linked chains won't dissolve, but merely they will swell, forming a gel. So, this is how by finding out the sol fraction and gel fraction, you will find out the degree of cross-linking, how much it is cross-linked. Subjecting the material to heat by placing in contact with a hot surface. Cross-linked polyethylene has more viscosity and resists flow. This is another way. This is solubility in heated organic solvent. The second one is subjecting the material to heat by placing in contact with a hot surface. Then cross-linked materials has more viscosity and it actually resists flow. Sol fraction and gel fraction. Commercial XLPE cables are normally have 70 to 80% gel fraction. This is what is known as degree of cross-linking. So, sol fraction is defined like this: weight of XLPE before dissolving, this using this organic solvent, minus after dissolving, divided by before dissolving. So, this is sol fraction. Gel fraction is weight of XLPE after dissolving by before dissolving. So, this is how sol fraction and gel fractions are defined, by which we estimate the degree of cross-linking of XLPE. These are the various methods of cross-linking. You can see peroxide and radiation cross-linking. We will study about them in the next few slides. Here, peroxide induced cross-linking. An organic peroxide such as dicumyl peroxide is added uniformly to the base polyethylene. The peroxide material's decomposition temperature is considerably higher compared to extrusion temperature, and thus it remains stable during cable extrusion. Because it has high decomposition temperature, it does not change during the extrusion process. But after extrusion process, when the cable enters a curing tube where the temperature is raised, the peroxide breaks down, releasing free radicals which pull away the hydrogen atoms from the polymer chains, and then thus allowing the cross-linking. So the unstable chains then combine to form a stable cross-linked polymer. So this is how, but of course it forms certain byproducts, but has high degree of cross-linking compared to other methods. Now here the phenyl group is indicated as pH. Now here this is dicumyl peroxide. This is dicumyl peroxide. When heated upon, so it will form free radicals which pull the hydrogen atoms off the polymer chains. So this is B, where it is cumyl alcohol, it can form with hydrogen. So then these free radicals will pull these hydrogen atoms, for example these two chains. From these two chains, these hydrogen atoms say have been pulled by these free radicals of dicumyl peroxide. So then after that, these two carbon atoms form a bond, like cross-link. So this is how cross-linking will take place due to dicumyl peroxide, but it leaves a certain amount of acetophenone in the material. Sometimes it is found to be reason for space charge accumulation in DC cables. Therefore, in DC cables, preferably alternate methods of cross-linking has to be used, has to be done. See, the other method of cross-linking is radiation-induced cross-linking, in which there are no by cross-linking byproducts in this case. But in this method, a beam of electrons emanating from a radioactive material such as cobalt-60 interact with polyethylene chains, forming free radicals. Again, that free radicals have to be formed, which lead to formation of active polymer chains like this. Again, this H. These chains interact with other chains, thus forming stable cross-linked structure like this. And but these forms no cross-linking byproducts, and but of course has lesser degree of cross-linking. The degree of cross-linking is less compared to the peroxide based cross-linking that just now we have seen. Now, temperature influence on insulation properties. The cable insulation in service has to encounter load cycling, which brings about a thermal cycling. At higher temperatures, the crystalline regions tend to melt and chain get farther, bringing about a reduction in stability as well as dielectric strength. So here the cable conductor temperature may go up to 130 degrees centigrade maximum, and insulation near the conductor shield here around 90 to 100 degrees centigrade is expected. So insulation near the shield is expected to have 60 to 70 degrees centigrade. Therefore, the cross-linked polyethylene, which has good degree of cross-linking, will not change its shape, will not get deformed, and then that's why cross-linking is also important for cable insulation. Now, copolymers. What are copolymers? Copolymers are polymers that are formed by incorporation of more than one type of monomer during the process of polymerization, to impact certain characteristics. Sometimes to impart certain characteristics, this is homopolymers, all are ethylene only. Like that is copolymers. You may have, for example, different kinds of polymers, monomers in the polymers. So these are called copolymers of this ethylene. So like that we have one or two important copolymers. So here the you see this linear low density polyethylene, LLDPE it is called, linear low density polyethylene. So this is ethylene, CH2CH2, C2H4 plus 4-methyl 1-pentane. So any longer chain alkaline would do actually. Usually butane 1 or hexane 1 or octane 1 can also be used. So this is using Ziegler-Natta polymerization method, and then this is how the structures are formed. Polyethylene co-4-methyl 1-pentane is also known as LLDPE. So this is the simple HDPE structure. This linear polyethylene, and then this is a low density polyethylene with branching, coiling, etc. So this is highly crystalline nature. This is amorphous plus crystalline in nature. So here this is in between actually. These chains are not of this much length. So shorter lengths of chains will be there in linear low density polyethylene. Compared to LDPE, it is much linear with significantly short branches. And it is shear sensitive because of its narrow molecular weight distribution and short branching. So it is more viscous and hard to process compared to LDPE, but less compared to HDPE. Because of less branches, there is less chance of entanglement during elongation, and therefore this LLDPE is used for thin films, and insulation tapes, etc. Are used by LLDPE material. Now ethylene propylene rubber is EPR, it is known. EP gum, sometimes it is called EP gum. Rubber is also called gum, so EP gum. So this is a copolymer of ethylene and propylene, 50-50 percentage normally. This is ethylene, this is propylene. So single molecular structure is shown here. Short chain branches like this, non-crystalline and amorphous structure. Needs reinforcing fillers actually. So needs to be cross-linked also. So if ethylene to propylene ratio is less than 50%, propylene segments inhibit natural tendency of polyethylene chains to align and crystallize. So therefore the polymer is more or less amorphous and very soft, not so hard. But if E by P ratio is greater than 50%, then the resulting polymer is semi-amorphous, semi-crystalline. So it is some portions are crystalline, some portions are amorphous, like that, if it is more than 50%. Pure EPR neither has physical properties required to perform as a functional insulation, nor it could be extruded into cable form. So therefore additives are required and fillers are required. So EPR has good dielectric properties. So its dielectric losses are low, only slightly higher than the actual polyethylene. But EPR with additives has better moisture prevention capability than cross-linked polyethylene. So these are the various material properties that are used in power cables. So we will see next testing of power cables, and then breakdown tests or insulation properties in our next videos. That will be the end of the portion of this semester. Thank you.